Welcome to solverfy.
35.6. We're told that the wavelength of a yellow sodium light in air is 589 nanometers, and air has roughly the same refractive index as vacuum, which is to say 1. Light travels very slightly more slowly in air than in vacuum, but for all practical purposes, most of the time it doesn't. The difference is negligible. And in fact, yellow sodium lights are often used, or have been used frequently, for like street lighting and stuff. They're probably getting replaced. I've seen them being replaced in some instances with LEDs or things, but I think they're still pretty common. I mean, if you go out at night and see a street light that's like a monochromatic sort of yellow color and everything looks kind of weird and colors are off, then it's almost certainly a sodium light. Anyway, we want to find its frequency. We want to find what its wavelength is if it enters some glass with a refractive index of 1.52. And then we want to find its speed in that glass using these two facts, the frequency and the wavelength. So the frequency is just the speed over the wavelength. And this doesn't change when it enters a different medium. Otherwise, we'd be out of luck in terms of trying to figure out anything. Because if the speed and the wavelength and the frequency changed, then one of them needs to be constant in order for that to be useful for us. And because the frequency depends on the actual time dependence of whatever process produces the wave, that can't change based on it propagating into areas where its speed is different. Is sometimes a slightly confusing fact for people when encountering this sort of thing for the first time. So the wavelength in our glass, it's going to get shorter because the wave points on the wave are arriving at the same rate, but they aren't leaving as quickly, so the wave gets sort of squished. And so this is 388 nanometers. Now, of course, we could just find the speed of light in the glass using its refractive index, but we want to use this again because it's useful to understand this. So let's call it n, is going to be equal to the frequency times the wavelength. So this will be 1.97 times 10 to the 8th meters per second.